Hello and welcome to session 6. In this session we're going to be looking at micrometeorology. This is basically how the air flows around the terrain and a little bit about convection as well. We're also going to have a quick look at some local effects that you might come across as a hang glider or paraglider pilot. So start out with airflow around the terrain. The first thing we need to understand about air is that it has weight and mass. In fact, a cubic meter of air weighs about 1.2 kilos. So when we're talking about moving air masses, we're talking about millions of tons of air very often. So we have to try and visualize how this is going to behave as it goes across the terrain. A good way of doing this is to visualize how a liquid, water if you like, would behave. It's not exactly the same. Air is much better at climbing slopes and things than water is, as it's much less dense. But the actual principle is very similar. So if you imagine white water, wherever there'd be white water over the terrain in front of you, that's probably where you're going to find turbulent air. So it's quite a useful starting point. So a good way to start with this is a bowl. If you imagine a site which is curved in a bowl, a good way to think about how the air is going to behave is to think about a bathtub. So think about the shallow end of a bathtub. If you get a bucket full of water and you sling it into that bathtub, it'll just spill up around the sides. Most people will be able to get that picture in their heads. And it's exactly the same with air. It actually will pour into the bowl and then spill up around the sides. So like this picture here, you get this characteristic airflow. It's important to us to understand this as pilots. First of all, quite a lot of flying sites are arranged in bowls of one sort or another. But when you go to the site, you might stand on the edge and think, oh, the wind is blowing straight on where I am, but actually the real wind above you could be 30-40 degrees different because you just happen to be in a bowl and it's being sort of focused in that area. So that's one point. Make sure you take off in the right place. The second thing is that although it's helpful to us in that the lift will go further around a bowl than on a flat ridge, as it were, it also means that you fly to one end and then turn around. You're often flying downwind on one beat down towards the back of the bowl, and then on the other beat you're also flying downwind. So there's a lot of downwind flying going on. Particularly if it's busy, that can be quite an issue. The other thing finally about bowls is, particularly in the UK, we fly some bowls which are really quite deep. And that means that you can fly on one side of it while the air is actually coming across a spur following on the opposite side. So you have to be a little bit careful. You can fly on a ridge perfectly happily. Because of the spilling effect, it allows you to get round the ridge quite a long way, and then suddenly you're into turbulent air from the other side. So just a little bit of understanding required of how the airflow behaves in a sort of bowl situation. Just generally, air, as it flows along, as I mentioned this, it can't change direction very quickly. It's got that in common with liquid. So if you persuade it to change direction over something like a gentle curve going up a hill or down a hill, then that's fine. You'll get a reasonable laminar flow. But if you actually, so this illustration here just shows a fairly sort of laminar, almost aerofoil shaped hill. So at the back of it, you've got sinking air, it's pouring down, but it should be fairly smooth. So it shouldn't be too much of a hazard, although not very good for you, obviously. If you want lifting air, and if you land there, you're going to land quite hard because you'll be in a sinking air mass. However, if you get a steep slope, particularly in a stronger wind, it's a different story. The air mass can no longer adhere to the curve. It sort of has a sharp edge, or the speed prevents it from sticking, and so it breaks up. You get a chaotic flow, and we call this a rotor or a turbulent area or whatever. Basically, it's chaotic flow, so the air is all mangled up as it tries to refill the low pressure. So that's actually really dangerous. It's marked on this one in red for a good reason. So if you find yourself behind a spine-back ridge or an obstacle in strong wind, you can expect to get very turbulent air. So obviously it's all about prevention, not doing that. Also on this illustration is shown the lift band. So a lift band is essentially a definition of an area where the air has a greater vertical component than the sink rate of your glider. So this varies slightly because some gliders have better sink rates, so they've got a bigger lift band essentially. And it varies on a slope because the vertical component's what's important, not the wind strength. So a cliff will have a bigger vertical component than a shallower slope and so forth. So that's the lift band anyway. So talking about cliffs, here's the same illustration here with the cliff edge. It's important to notice this because cliffs, as we've just established, are a good place to find lift, but they're a bit hazardous because if you go back behind the edge, as is illustrated here, the turbulence starts right behind the edge because of the inability of the air to change direction quickly. In fact, if you look at the cliff edge there, it's pretty much the same as the ridge we just looked at, just tilted over a little bit, and the same thing applies. In fact, in this illustration, that red area isn't big enough, really. It can reach back quite a long way behind the cliff edge. So, good for lift, not so good for turbulence, which means if you're taking off somewhere where there's a cliff edge, you really need to find a nice rounded bit to take off. If you're on a paraglider and it's a steep edge like that, it's almost impossible to launch. If it's a hang glider, it's not too bad. You have to shuffle to the edge and hang your toes over the edge and dive down, which is you need help for. So cliff launch is a little bit iffy, but what people often do is they take off a nice rounded bit, fly to an area where there's a vertical cliff so they get the lift, and then think about top landing there, which is obviously a mistake for obvious reasons. So turbulence behind obstacles, same thing on a smaller scale, really. Airflow around a conical hill. Well, when they build bridges, they build the pillars that go down into the water round rather than square, or other shapes as well. And the reason is because they know the water will then spill around. And the same happens with a small hill. So if you get a little lump somewhere, the air will try and spill around it. So it's just worth understanding that. Just because something is big or tall doesn't mean it's going to have very good lift. You actually need a reasonable surface that will encourage the wind to climb up over it, or the air mass. Also worth mentioning about gullies. Same thing, going back to the bridge analogy. If you have two pillars, then the water will accelerate through the gaps, and it's the same here. So if you get two hills and there's a valley between them, the air will pour through that, and because of the Venturi effect, you will actually get stronger winds there. So just worth knowing about. So ridge lift, we've just mentioned this is about the vertical component. This means that when you're flying a ridge, the steepest part of the ridge has the highest vertical component of the air. It's not only about steepness in terms of physical steepness, it's about how fast the air is going up. So that also has an effect when we talk about the wind being off the hill like this. So you get a very steep hill, but if the wind is coming up at an angle, we've all walked up a hill, a steep hill at an angle, and it takes you longer to get to the top because you're taking a more gentle climb. So the vertical component is less. And the same, so if the wind is off the hill a little bit, then we get the disadvantages of strong winds, but we still get but we don't get the advantages of the lift because there's not much lift either. And the further off the hill the wind goes, the less lift there will be. When you're flying a site and the wind is quite often off, or off part of the site, it does introduce a hazard as well. First of all, apart from the lack of lift, you have the upwind and downwind beat situation. So when you're going more or less on the interwind leg, you're going with very slow ground speed, which is quite handy if you want to slide in a top land or something like that. But when you turn, you're making a downwind turn. So you're suddenly whizzing along very close to the hill if you're not very high, with very high ground speed. So pilots sometimes react to this, but they're going very fast by slowing down a little bit, either like that on a paraglider or eating out on a hang glider. So they go a little bit slower on the downwind leg, which is a mistake. Because although you're travelling fast over the ground, the aircraft is actually still flying quite slowly if you haven't got much airspeed. And then if you start to sink, so the slope is over there, you're sinking, and you think, oh, I'm going to hit that, and you try and make a tight turn. If you're flying slowly and you make a tight turn, it all goes to worms very quickly. You can quite easily spin or lose control of the glider. So when the wind is off the hill, especially when you're on a downwind leg, you need to be very cautious and make sure you maintain adequate airspeed so that you can get out of there if you need to. So we've established here what we need to look for in a flying site. We want it to be into the wind, obviously, as square as possible. We want it to be as steep as possible in order to generate lift. Reasonably smooth. We're not too worried about that, but obviously if there's lots of bowls and spurs and things, it's not be as good as a smooth side. And large. Large is just very simply, you get a couple of cubic kilometers of air going up. It's actually easier to use the lift than if it's just a tiny little bit. Ideally, it should be clear of any obstacles as well. Obviously, physical hazards such as power lines, things like that, trees in the way. And of course, airspace is another thing. The site is one thing, but the air above it may be used by somebody else. So we need to make sure that our sites are clear of airspace, or at least we know where any airspace is. So that's a good flying sight, really. Wind gradient. Okay, I've already mentioned that air has mass and weight. So as you drag along your, a million tons of air along the surface of the planet, the stuff at the bottom has to get dragged through all the grass and the buildings and all this sort of stuff. So it slows down. It's as simple as that. It keeps being interrupted by things, so it's just like sandpaper, if you like. So what this means is that at low level, the wind speed is relatively low. If you were to sort of put up a big pylon or something, you climb to the top of it 200 feet high, assuming there is any appreciable wind, it's always going to be windier at the top than it is at the bottom. So that's wind gradient. The first couple of 100 feet particularly, you notice this. So why do we care? The principal thing is that if you're coming into land and you're coming in on a headwind, then your glide angle might be fairly poor. But as you come down, the headwind reduces, your glide angle is going to improve over the ground. So your glide will flatten out and you'll start to accelerate. So that's fine as long as you're ready for it and you don't, misjudge your glide by overshooting or try and slow down too much. You have to keep your speed on as you come in. So it's just about judging the wind gradient. And some sites, especially if they've sort of got trees or something upwind or in their little dip, suffer a lot from wind gradient. So there's quite a significant gradient as you come in. This usually happens if there's an open aspect out ahead of you. If it's a valley, then it can be quite a different situation. Okay, so that's wind gradient. Another thing about wind gradient, of course, is that it's going to be windier higher up. So if you're halfway up a hill and you think it's a bit windy, I don't want to fly from the top, I'll take off from here. Bear in mind, obviously, it's going to get windy as you take off. So this has happened to pilots who haven't really taken enough account of it. They've gone up and then got pinned in strong winds. So that's wind gradient. And what I was just talking about there on hills is exacerbated because of this, the Venturi effect. Okay, so the Venturi effect is you get a big air mass here and it hits a hill. So it does go up the hill, it rides up, but the upper air tries to carry on in the same direction. As I mentioned, still got mass. So effectively, it gets squashed as it goes over the top. So it's like a narrower tube, if you like. And like any gas or liquid, air will accelerate at that point. So to us as pilots, that means that someone who's at, say, 300 feet off the ground out in front of a hill might be flying in a, in this example, at ridge level be sort of 18 km/h wind. But if they're actually on the crest of the hill, that could be 25 km/h or more because of the Venturi effect. So it's possible to be standing on the edge of the hill. People out there seem to be flying, not having a problem, but it's too windy to take off. So just as long as you're aware of that. The other thing, of course, it affects you if you want to land back on the top of the hill again. There is always going to be a stronger wind just over the brow of the hill. Okay, so that's the Venturi effect. So we have to talk about safe wind speeds. So what is a safe wind speed to fly in? Well, we're talking about micrometeorology, so I'm going to say 0 to about 16 miles per hour, or you can convert it into meters per second or kilometers per hour, whatever you like, is reasonable. You can fly in slightly stronger winds than that, but you start to run into issues as it gets windier. Not only just the wind strength increase, but the turbulence increase. If you double the wind strength, you square the amount of turbulence. So all those things we were talking about earlier, like turbulence behind obstacles, wind accelerating through gullies, will become much more noticeable in strong winds. So try and avoid really strong winds if necessary. Obviously a hang glider's got a slightly higher top speed than that, but actually launching hang gliders in absolutely zero wind is a bit of a mission. You need a sort of steep ramp or good pair of legs to do it. Okay, should be the correct direction for the site. It's no good trying to take off while the wind is miles off the site, obviously, as I'm sure you're aware. But the critical thing is gusts. If the wind is varying in direction, so we've got a windsock or something and it's varying by 20 or 30 degrees, there must be a reason for it. It's usually because the air is slightly turbulent, and also if it's varying in strength. So if the wind is going 12 to 14 miles an hour over a minute, then that's fine. But if it's going 6 to 14 miles an hour, which is sort of more than 100% increase in a minute, then it's a guarantee that it's going to feel quite choppy and turbulent when you get up there. So it's worth waiting for a little while and just seeing if that is the case. If it's going from 6 to 14, it's not too difficult for it to go to 20 as well. So it's worth hanging on for a little while and watch a few other people fly, let more experienced pilots tell you how it feels. So gusts are a factor that we need to be very careful of. Okay, anemometers, wind speed indicators. I've talked here about a couple of things to do with wind speed. So how do we measure it? Well, you can have a little anemometer. What are they for? Right, the reason that someone has an anemometer is so that they can follow a trend. So they check the wind speed, and then 20 minutes later they check it again and they say, oh yeah, it is gradually increasing or it is gradually dropping. If you think it's too windy for you to fly, but your anemometer says, oh, it's not that bad really, then it's too windy. They're really a confirmation of what you should already know, really, and just to put some numbers on it helps you build up an understanding of the wind speed that's, as you build experience and fly on different days, if you match it all the time to what your readings are, you'll have a good idea. Right, anemometers. We've got two here. One of them's got a little sort of vane on the top, and they're great because it doesn't matter where you hold them, they will get an accurate reading. But some of them have got sort of a little impeller or whatever it is, and you have to be careful how you use those, because if you twist your hand slightly or you point them too far down or too far up, they can underread a little bit. So the best thing to do is to keep your anemometer out, take a few wing readings over a period of a minute or two, and the highest one will be the most accurate. And the reason for that is obviously you can have it slightly out of wind or slightly too much of an angle or something like that, and you can make it underread, but you can't make it overread, not you run fast towards the edge of the hill. So the highest reading is likely to be the most accurate. Okay, so that's anemometers, useful things to have. Sea breeze fronts, it's a local effect. So what's a sea breeze front? It is essentially as the land warms more quickly than the sea, so anywhere that's fairly warm, we will have a situation where the air density over the land reduces and the air will become buoyant and start to lift. But you've got cooler air over the sea because the sea cools up more, warms up more quickly, more slowly. So the cooler, denser air mass will then slide in underneath like a mini cold front in order to replace the warm air that's going up. So this obviously happens on the coasts. Now, some coasts where the sea is cold and the land is warm, it happens all the time on an everyday basis. But in the UK in particular, we tend to find it happens on warm summer days when there's a light wind. So it doesn't matter if it's a light onshore wind or an offshore wind. If it's a light onshore wind and then you get a hot day, it'll often pick up during the day as the sea breeze builds. If it's an offshore wind, there may be no wind or a slight offshore wind, and then that'll die off to nothing, and then maybe you'll get a light onshore wind later in the day. If you're flying on the coast, then obviously if the wind picks up, that might be useful to you. It depends what the background wind is. If you're flying inland and you're flying towards a coast, so you've got a sight with a coast pointing up a direction shortly a little way behind you, what can often happen is you're flying there merrily in the morning and then the sea breeze pulls in and the wind switches direction. That's a number of things, because it's cold air as it comes in, cold moist air usually, it will actually kill any thermal activity. So if you're on a north-facing site and you've got a south-facing coast behind you, you've got a limited amount of time on a warm day before the sea breeze will affect you, and so forth. So that's sea breeze front. The terrain that the sea breeze, the cool air has to come in over, has quite a big effect. So if it's flat air, like the east of England, it just tends to roll in really, and it can go quite far inland. If it's a place where there's a coastal site or there's some moorland or some high terrain just inland, then the air might try and split round it, but if it does go up over that, you can actually get usable lift. So if you have an offshore wind and a sea breeze, especially if there's a bit of rising terrain, you can often get a convergence line, so a line of lift. So this has been used in the past by pilots, say flying cross country towards a coast, and as they're going there, their thermals peter out, and you see blue sky ahead of them or a line of haze where the sea breeze is, and just before they get there, there's a line of cloud, and they can use the line, basically turn right or turn left, and surf along the sea breeze convergence. So it can be useful, but it's all about timing and the right terrain underneath you. Right, convection. So convection, we're talking here about thermals. So as we know, the air heats the ground heats the air, and off we go. You get thermals forming. There are various prerequisites for good thermal formation. I talk about that in a separate session about lapse rates and that kind of thing. But all we need to know at this point is that if we have cumulus clouds, bubbly clouds, then they're being fed by columns or bubbles of warm air that are thermals. As you lift a few tons of warm air up in the air, then it's a bit like taking a bucket full of water out, going back to the bath analogy again, everything else slumps in to fill the space. So when you're flying, you will get lifting air in the thermal, and you'll get sinking air sinking down and going towards it, just around it. So it's quite useful when you're flying. You tell the difference between a gust and a thermal. With a gust you get pitched backward, and with a thermal it tries to sort of suck you in, as it were. But you do have that interface of air travelling in different directions, so it can be quite turbulent. And in strong thermals, the turbulence can be quite hard to deal with. So you can tell how strong the thermals are by a number of factors, and one of them, if there's cumulus clouds, is how high the clouds are building. Great big towering clouds means strong thermal activity. On this diagram we've shown a dew point here. So the warm air goes on, it's full of moisture. As it goes up it cools and cools, and eventually can't hold the moisture anymore, so the dew point temperature is where it condenses out and where you see the cloud. It is possible to have thermals where the thermal never reaches dew point, so there's kind of blue thermals, but in the UK there's usually cloud on top of thermals. So there's a good illustration of one. This is quite unusual. This is a fire, obviously, so pyrocumulus if you like. So you can actually see the smoke marks the rising warm air. Obviously it's black because it's smoke full of dust and soot and what have you, but when it reaches the dew point temperature and all the water vapour condenses out into visible droplets, they're obviously white. Well, a bit stained, I think. So it's quite a nice little illustration of how a thermal is. And you can actually notice from this picture that some of the other clouds there are quite small and not very well developed. So obviously the fire has added a bit of extra heat to the system, which has given this one a good impetus to generate a significant cloud there. Okay. All right, so that's a basic introduction to micrometeorology, airflow over the terrain, round obstacles, and a couple of local effects and convection. I hope you found that useful.